Hello, I'm Nizhou Wu from TU Delft. The title of my thesis is Testing STM Manufacturing Defects for Models and Test Solutions. We collaborate with IMEC where we get STM measurement data and corroborate our designs and tests. The industry is commercializing STM. A lot of companies all over the world are investing in this technology, Intel, Samsung, F-Spin, etc., etc. And we know testing is the last chance to check and guarantee the required IC quality. But there is no dedicated test solutions existing for STM. For today's commercial test solutions, there's a very important assumption where any defect inside a semiconductor device is modeled as a linear resistor either in parallel to the device or in series with the device. Here I show you some measurement data of a good STM device and a defective STM device. This suggests that STM devices have unique device defects which are intrinsically nonlinear. And so there is a gap between nonlinear device defects and the conventional linear resistor model. So therefore, we need to close this gap, and we need to develop dedicated test solutions for STM. The contributions of my thesis can be divided into three parts. In part 1, we survey the STM manufacturing process and all possible defects that may take place in each step. Then we apply the conventional test approach to interconnect defects. In other words, we model interconnect defects as linear resistors, such as opens and shorts. To close the gap between nonlinear device defects and the linear resistive model, we propose a new test approach which we name as device-aware test. DAT specifically targets device internal defects. Therefore, DAT can give us high-quality yet cost-efficient test solutions. We apply DAT to three key types of STM device defects based on silicon measurement. And these defects cannot be detected by the conventional test approach. There are pinhole defects, synthetic antiferromagnet flip defects, and intermediate state defects. In part 3, we propose a magnetic coupling model. Using this model, we can evaluate the impact of magnetic coupling and density on STM performance. In addition, we also propose a magnetic field-aware compact model of perpendicular MTJ. Using this model, we can design spintronic circuits along with CMOS circuits in an accurate, fast, and efficient manner. Here you see the bottom top STM manufacturing process is compatible with the conventional CMOS process, and MTJ devices are fabricated and integrated into two adjacent metal layers. We classify STM manufacturing defects into front end of line defects and back end of line defects. For back end of line defects, MTJ device defects are extremely important since they are unique to STM. Here we list them in the order of importance. These defects can never be catched by the conventional test. Therefore, we need to apply device-aware tests to develop dedicated test solutions. In the conventional test approach, all defects are modeled as linear resistors. This test approach is still valid for interconnect defects. We injected all possible resistive defects in a 1T1 MTJ cell. Then we performed comprehensive circuit simulations to derive single-cell faults. On the right side, I show you some fault modeling results for bridges. Our simulation results show that resistive defects result in easy-to-detect faults. To detect these faults, we can simply apply March tests, for example, March C-. But the reality is not so simple because STM devices are also subject to manufacturing defects, and these unique defects require new test solutions. We propose a new test approach called device-aware test to specifically target device internal defects. DAT consists of 3 steps, as you can see here. The first step, defect modeling, is a key difference from the conventional test approach. In this step, we first physically characterize and model a device internal defects. We incorporate the effects of defect into technology parameters of the device. Then we map the effective technology parameters into electrical parameters of the device. This gives us a defective device model. We can also use the collected silicon data of the defects to calibrate and optimize our defective device model. The second step we do is fault modeling. In this step, we first extend the conventional fault space to make it cover all memory faults for non-volatile memory technologies. Then we perform a systematic fault simulation procedure to derive accurate and realistic fault models in the presence of defects. Here I want to highlight on the defect injection step. Instead of just adding a linear resistor, we replace a defect-free device model with our optimized defective device model. Based on the fault models we get, we can develop corresponding test solutions. For easy to detect faults, we can simply use March test or memory beast. For hard to detect faults, we need special DFT designs or stress tests. Here I show you a case study of device zero test for STM-RAM. Pinhole defects are a very important type of STM-RAM device defects. It takes place in the MGO tunnel barrier during multi-layer deposition. In the first step, we comprehensively characterize the pinhole defects and develop accurate defect models for pinhole defects. In the second step, we perform fault modeling using SPICE-based circuit simulations. Our simulation results show that when the pinhole size is larger than 0.35%, it results in easy to detect faults. When the pinhole size is smaller than 0.35%, it results in a hard to detect faults. We also compare the fault modeling results using device zero tests and using conventional tests. Clearly, you can see our device zero test results in unique and realistic faults, while the conventional test leads to wrong sensitized faults. Our device zero test can lead to reduced test escapes and optimized tests. However, the conventional test approach results in test escapes, and therefore they cannot detect small pinhole defects. In the third step, we can develop test solutions based on fault modeling results. For easy to detect faults, we can simply use this March element. And for hard to detect faults, we propose to use hammering right-wrong operations to detect small pinhole defects. This is another case study of DAT. Synthetic antiferromagnet flip defects mean that both of the magnetizations in the reference layer and hard layer flip to the opposite direction. Some measurement data about the defects. Our fault modeling results show that a SAP defect leads to an intermittent fault. To detect such a fault, we propose to use March algorithm with magnetic rides. To the best of my knowledge, we are the first in the community to propose magnetic March algorithm. This is a third case study of DAT. We observed that intermediate state defects lead to intermittent right transition faults and require dedicated test solutions. In part 3, we explore robustness analysis of STM design. More specifically, we propose a magnetic coupling model. Magnetic coupling is a critical design constraint for high-density STM-RAMs. We propose a intercell coupling factor psi to indicate the coupling strength in a dense STM-RAM array. We also quantify the impacts of magnetic coupling and density on STM-RAM performance. In addition, we propose a magnetic field-aware compact model of perpendicular MTJ. This model is based on physics. It exposes the simulations of process voltage and temperature variations. You can also configure different magnetic field sources. Using this model, you can do electrical and magnetic simulations of MTJ and CMOS hybrid circuits. My thesis has the following industry impacts. First, it enables fast and robust STM design and verification. Our magnetic coupling model helps you maximize STM density. Our compact PMTG model enables fast and efficient spintronic circuit designs. Second, our device zero test approach can lead to test escape reduction and quality improvement. This is mainly achieved by accurate defect and fault modeling. As a result, you get high-quality test solutions. And third, DAT is very helpful for efficient year learning. This is because defects now have unique fault signatures. And fourth, DAT also helps for test time optimization. And finally, divisor test is a generic approach. It can be applied to other memories such as VRAM, PCM, and VRAM. It's also applicable to logic circuits at advanced technology nodes. Let me summarize my presentation here. Based on my PhD research work, I have 13 peer-reviewed papers, including 8 conference papers and 5 journal papers. The 8 conference papers include 3 ITC papers in a row, 2 date papers, 2 ETS papers, and VTS paper. 5 journal papers include TTTC 2019, TVSI 2021, and 3 submissions this year to TC, TCAT, and GETC. During my PhD studies, I've also received 5 awards, including a Best Paper Award at Day 20, a Distinguished Paper, and Best Paper Award candidates at ITC 20. The Best Paper Awards will be announced at ITC this year. I've also received 2 Best Paper Award nominations at Day 21 and ETS'19. And this year, I graduated cum laude at TU Delft, which is a great honor to me because only less than 3% of TU Delft PhDs get this honor. If you are interested in my research work, you can download my PhD thesis book for free. And this is a detailed list of my publications. In the end, I would like to acknowledge my colleagues at TU Delft and our collaborators from IMEC. Thank you for your attention.